All right, welcome everybody. This is week 2. This is module 2. We are going to be working on the gas laws. We're going to be talking a lot about different gases and pressure, volume, temperature, things like that, how they interact. To start with, talk about what the states of matter are. Okay? Basically, there's 3 states of matter. There's gas, liquid, and solid. And when we talk, we are going to assume that we are talking about gases that are at room temperature and regular pressure. Okay, so at room temperature and regular pressure, just atmospheric pressure, okay? State depends on bonds, ionic, covalent, and forces. And these, of course, are our IMFs, intermolecular forces. So if we take a look at the first one, the first gas we're going to look at, these are mostly non-polar molecules. So they're non-polar, they don't have any attraction to each other. So they are nonpolar, they fly around at regular room temperature, okay? Also on your notes, you saw this paper. And this paper tells about the states of matter, okay? So for our gases, we're gonna say that the particles move in an independent manner of one another. They move in a random manner. They go in a straight line till they collide. So this guy is just going to go till he hits a wall, and then he's going to bounce off, and he's going to clip that guy, and he's going to bounce off this way, all the time that these other ones are also going up, hitting a wall, bouncing down. They're all going in a random straight line pattern. And they go until they hit something, and then they bounce off. They assume the shape and the volume of the container, meaning that no matter how much gas you put in here, it's going to spread out and be in every area of the container. Okay, so if we were in class, we would write this all right here. But as long as you look at this and look at this, then you're good to go. Okay? Next are liquids. Liquids are mostly polar molecules. And large mass. Nonpolar. So, not polar molecules have an attraction. So instead of flying around randomly, they're going to be attracted to one another. Large mass have such a big mass that they don't fly around. Gravity affects them more. Imagine if you took all these and boom, stopped their motion, they'd all fall down. They're just rolling around each other. Okay? If I stuck my pen in here, I could put them in between the molecules and they would go down. They would roll around out of the way. So here, these guys are just woo, 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 bang. These guys are touching, but they're rolling around each other. It's kind of like a ball pit at McDonald's or Chuck E. Cheese. If you dive into this ball pit, you would force these out of the way and you would sink to the bottom. Okay? So liquids, particles which are much closer than the gases, they slip by one another. They roll around on each other. They have a roll around each other. They have a definite volume, meaning if I put in 100 milliliters of water here, it'll always be 100 milliliters of water. If I put it in a bigger container, still be 100 milliliters. Okay? The thing is that it assumes the shape. So if I went from a square beaker to if I went from a circular beaker to a square beaker, it would be in a square shape, but it wouldn't rise up like the gases did. Okay? So lastly, we have solids. And in our solids, these are mostly ionic. And metals. Okay? And these have a matrix. These are attached to one another. Those two will always be next to one another. If I picked up this whole thing and flipped it on its side, number 1 would always be number 2 and be next to number 2. So there's like a matrix. Okay? They're linked together. Solids, the particles occupy a fixed position. They're arranged in a definite pattern. Okay, they vibrate around a fixed point because they still have motion. They just don't have movement related to one another. They have a definite shape, definite volume. Okay? So the one thing I did want to add is that these polar molecules and large mass nonpolars, they can be liquid or these guys can also be sometimes solid. Okay? So these are the characteristics. Looking at this, these gases assume the shape and the volume of the container. Polar molecules assume the shape, but they have a definite volume. Putting them in a different container will not change their volume. These do not assume the shape, do not assume the volume. They have a definite shape and a definite volume. So look over these pictures when you're looking these notes, and I think you're going to have a good idea of what's going on there, okay? Now the last part of this, because we just talked about motion, let's talk about how temperature affects particle motion. Okay? So, let's take a look at this and say, what is temperature? Well, temperature is the average kinetic energy of particles in a material. Okay? So temperature is the average kinetic energy of the particles. Now, if you remember, kinetic energy, there's two types of energy. Kinetic, and there's kinetic energy, which is the energy of motion. So things that are moving have kinetic energy. Kinetic energy is based on motion. There's also potential energy. Well, let's hold off on kinetic energy for a minute, and let's talk about this graph. Okay? This graph has temperature across the bottom, and it's got the kinetic energy of the molecules. So this front scale is called the Kelvin scale. It's based on absolute zero. Okay? So what is absolute zero? Basically, absolute zero is when all molecular motion stops. right? So temperature is average kinetic energy, which is motion energy. If it stops, then it has to be at zero. Because if the motion stops, the temperature can't go any lower. So that's why it's called absolute zero. Okay? Remember, even solids, the ice cubes in your freezer, the molecules have vibrational motion, so they are moving. And we know as things get colder, things move less and less and less as things get colder. Okay? So in the back here, this back scale, which is the big dotted line, that's Celsius. So we know 100 right here is boiling. We know 0 is freezing. And we know that absolute 0 is minus 273. Now, it's theoretical, of course, but they just extrapolate the motion and decrease the motion, and they extrapolate to minus 273 degrees C. That would be all energy stops. Well, this Kelvin guy, he came and he said, I need a new scale. This won't work for me, okay? And what he did is he said, I'm going to change it. I'm going to change absolute 0 to be actual 0 on my scale. He went up the same amount. It's got the same slope. An additional 1 degree C is the same as adding 1 Kelvin. So from minus 273. So what you're looking at is for every change of 1 degree Celsius, you have a change of 1 Kelvin. All he did was shifted this scale so you went to 0. So kelvins, if we look right here, and it's not degrees Kelvin, or it's just kelvins. Kelvins equals degrees C plus 273. And 1 degree C is the exact same temperature change as 1 Kelvin. So what? Why did he do this? Okay? Well, basically, what does Kelvin not have? Absolute 0. Can't get any lower. Kelvin puts 0 there. Kelvin has no negatives. No negatives on the Kelvin scale. Because what you're going to find out is when we talk about temperature and pressure and things like that, if you had a negative temperature, the gas laws would tell you you would have negative volume. And volume is the amount of space taken up. Can you have negative volume? No. You can't. Okay? So that's why his scale is the exact same, except it just starts at a different number. That's all. But we have to use kelvins in the coming 2 lessons. Okay? So remember, temperature is kinetic energy. When temperature goes up, the things are moving faster, the energy of motion. Okay? So here's where we say KE is equal to 1/2 mv squared. And that's where m is mass and v is velocity. Okay? So, thinking about your algebra, if I keep kinetic energy the same, if I do not change kinetic energy at all, if this number is bigger, this number, the m is bigger, the v has to be, to get the same KE, I'd have to make it smaller. Okay? So if something's big and fat, the v velocity has to be lower. Now, remember, at same kinetic energy, oops, energy, which is same temperature, right? At the same kinetic energy or the same temperature, more mass equals slower speeds. So if your total's the same, if one of these goes up, the other has to go down. That's what this shows you. This graph's kind of confusing. This is the fraction of particles, the percentage of them. How many are going, this is a lot, are going at this speed. So of your oxygens, let's say the most popular speed is right here. Okay? Of your waters, the biggest fraction of them, most of them, are at this speed. The heliums, most of them go at this speed. And the hydrogens, the most common speed is right there. Okay? So, take a look. Weight. Oxygen's the heaviest, going the slowest. Hydrogen, the lightest, has the overall speed at a highest level. Okay? This is true when all at same temperature. Okay, so when they're all at the same temperature, that's the important part. When they're at the same temperature, they have the same kinetic energy. The bigger the M, the lower the V. The bigger the M, the lower the V. Okay? So if you just remember, biggest molecules move slowest, and things are getting in the way here. I'm trying to write smallest molecules move fastest. Okay? So that's kind of a basic introduction on how temperature and particle motion work, how gases and liquids and solids all work to, how they're different. And we're going to be specializing in gases now, and we're going to be specializing in the gas laws in units in video lessons 2 and 3. Okay? So review over this. This information will be on the test, and come back. There's no practice really. Come back when you're ready for the next lesson. Okay? See you guys. Bye-bye.